Hi, good morning and good afternoon to those of you joining us from a little bit further east, and thanks for joining us for the Zippertubing EMI webinar. I was really excited to see some familiar names signing up for this, some people that I've worked with in the past and currently working with on projects. I know, Madison, you saw some people that you recognized signing up for this too, so very, very exciting to be doing this. For those of you that I haven't met, my name is Matt Hesselbacher. I'm a principal engineer here at the Zippertubing company. My background is in electrical engineering, and I've been working here at Zippertubing for a little over 6 years. And I do mostly product design, specifically for cable protection, component protection, including EMI shielding. And with me today is Madison Lenschow. She's a design engineer here. Her background is in mechanical engineering, and she does the same, product design, product development, including EMI shielding. And she's been working here for 2 years, over 2 years.
Just a little over,
yeah. That really went by quick.
It did.
Yeah, so we're here today to talk about EMI. So we're going to start with a little kind of basic overview, talk about different types of interference you might see. Then we're also going to get into steps to identify what type of interference you might be up against, and then also some troubleshooting steps. So these are things that come up a lot when we're talking with people. So we're going to give you those tips, things that we've kind of learned to look out for, and you can try to identify the cause of your issue and maybe even get pointed towards a solution, or maybe even solve your problem by using these tips. Then we've also got a couple demonstrations, sort of visual ways to visualize what we talked about here, and including a demonstration of a shield in action, attenuating a signal, and how that might work and how it looks. So I think that's going to be real exciting. So definitely stick around and watch that towards the end. And we've also built in a lot of time at the end for questions. I know some of you might have some questions that you wanted answered, or maybe going through this you might realize there's some questions, or you'd like us to talk a little bit about one of the topics. So we've got plenty of time at the end to do that. And then also wanted to make you aware that we will be sending out our contact info and a version of this webinar. You'll be able to watch it later if you do have to step away, or if you want to watch it again, or send it to a colleague that couldn't join today. We'll make that available for you to watch at a later date, as well as our contact information after that. So with that, I'm going to turn it over to Madison.
Thanks, Matt. So yeah, we're going to start with the basics here. What is EMI? So EMI stands for electromagnetic interference. Sometimes you will see RFI. That stands for radio frequency interference. The two terms are used interchangeably, mean the same thing. I'm going to be saying EMI today for the webinar. And what that is unwanted noise in your system caused by different electrical components. So it could differ. It's not always the same results you're seeing when interference comes up. It could be some minor interruptions, and this interference can go as far as to damage the system and make components unusable. And it is something we're seeing more today, right, Matt?
Yeah, I think so. And it's probably a combination of different things, right? It's in previous generations, more things were mechanically driven or pneumatically driven, but now those systems are being replaced with electronic components, and they're also getting, of course, smaller, more lightweight, more power efficient, so they can be more. They can be everywhere, right? They can be more mobile and used all over the place. So that's why there's more sources for EMI and more components that can be potentially damaged by EMI.
Right. So when we're talking about EMI, there's two types. We've got magnetic or H field interference and electric or E field interference. Electric, that's going to be your mid to high frequency range, usually like megahertz, gigahertz. Magnetic is going to be more low frequencies. I typically see it in the hertz, low kilohertz range. And then electric, got a couple analogies here. I like to think of throwing a rock in a lake. Electric spans great distances and dissipates slowly, kind of like the ripples you'd see on water after throwing a rock in. Those ripples might get smaller, but they're going to go very far. And magnetic, easy to remember. I like to think of a bar magnet. Just like those magnetic field lines on a bar magnet, the interference is very strong right near the source, and then it's going to dissipate pretty quickly with distance as you get far away from that source.
So you kind of talked about the two different types, electric and magnetic. But typically it would be one or the other, or it would be, maybe one thing could be generating a magnetic field interfering with you, and something else could be causing an electric field. You wouldn't normally see something causing both, right?
Right, not both coming from the same source.
Right, so you'd want to tackle the thing that's causing the magnetic field interference first, identify that problem, and then you could work on the electric field if you're seeing both. But typically we'd see it's one or the other causing the problem.
Right. Okay, so now that we kind of know the two types, how do you know what you have in your system? We've got a few steps that you can take to identify, pretty simple steps to take. First thing you're going to do is locate those affected cables. Figure out what's giving you interference, what you're seeing problems with, usually a signal cable. And once you've identified that cable or component, you want to determine if there's any high current power sources nearby. If there is, you want to separate your affected cable from that power source. As much distance as possible, like we talked about, it diminishes that interference with distance.
Right, and you say, more distance the better. Like, what are we talking about here? Is this, a couple inches? Are you talking yards? Like, how far should they kind of look at?
Typically, to start, I recommend even a foot, 2 feet. Gaining a little bit of distance is going to knock down that interference if it's magnetic. So do what you can. If there's anywhere where those cables can't be separated and they do have to cross them right at 90 degrees, and that will cancel out the field. But if you are seeing improvements, then it's likely that you're dealing with magnetic interference. Now, the next one, this is a fun one. We're going to be looking for electric interference. And what you want to do is just grab some household aluminum foil, wrap your cable that's being affected really tightly. You don't want to leave any gaps in there, anywhere where you don't have it wrapped, or if it's not end to end, that's going to let the interference in. So make sure you have a really good wrap on that. And what you're doing is creating an EMI shield. So if you're seeing improvements, you can be confident that you have electric interference. And it's not good for permanent shielding. This is really good to just figure out what you've got going on. But the aluminum foil wouldn't be a good permanent shielding solution, but good to figure out what you got.
Yeah, and also when you say, put the aluminum foil on, that's just to figure out if it's an electric field interference, right? If you put the aluminum foil on and it's not making any bit of a difference, it might be magnetic.
Right. And
the same for the other troubleshooting, right? If you're moving your cables around and you don't see any difference, that means probably an E field and not a magnetic field.
They're pretty independent. The foil or a shield would not help with your magnetic, but it would be a good indicator that it's electric.
And even if you start to see some improvement, then you're on the right track to getting your problem figured out.
Exactly. So now that we know, once you figure out what you've got, we're going to figure out how to knock down that interference or how to attenuate that interference. So this is going to be dependent on your specific application, depending on what route you take, due to factors like environmental concerns, the temperatures you might be seeing in your system, or possibly chemical exposure. A big one that's going to determine what kind of shield you use is the flexibility you need in your system. And so when we're talking about electric, there's a couple different types. We've got reflective materials. These are made of conductive metals. And just like it sounds, the interference is going to come in and get reflected right off. And then the other type is an absorptive material.
Right. So we've got listed as carbon there, but the absorptive materials are really a foam or a silicone or some sort of polymer that has those elements in it that are going to attenuate or disrupt or absorb some of the signal as it's passing through rather than reflect it away.
Yep. And then when we're talking about magnetic, just like we did with the test, the solution can just be moving those cables. If you're able to reroute them, avoid parallel runs with those power cables and your signal cables. Cross them at 90 degrees where they do have to go past each other. If you aren't able to move those cables around, you can use a ferrous metal, like a thick steel.
Right, yeah, we've listed steel here. That's the most common one. Sometimes we'll recommend that just because it's readily available. Many people can get it quickly or easily put it in there. Mm-hmm. There are other options. You could use a special alloy with a ferrous metal content, something with a lot of nickel in it or something. These ones are more rare, maybe not as cost effective, but there are certain situations where you would need that, right? If you are really space constrained, or if you really
have to.
Yeah, you need to cut every bit of weight that you can, and you might need that. But typically, steel is a good solution for these ones.
And hopefully you can get away with just moving the cables.
Right, ideally. All right, great. Now we're going to go into the first demonstration or visualization. This is a real cool one. I like this one. It's a good way to kind of, visualize the concepts that we've been talking about a little bit in a fun way to really.
Yeah.
Yeah.
So this is our fixture. This is going to represent different shielding materials, and we're going to see how various materials work to shield different frequencies. So our top level here is going to mimic a material that's got some visible openings, maybe some kind of a knitted wire kind of shield. The middle here is going to be something with smaller openings, maybe like a porous surface. You might not even see those openings, but they're there. This could be something like a metallized fabric. And then on the bottom here, this is going to be something more like a solid sheet shield, something like a foil, just like that aluminum foil we talked about with the test. So those are our three kind of materials. And we have various spheres that are going to represent our frequencies. So large red spheres, that is going to represent our low frequency interference, which has long wavelengths. And then we've got small blue spheres. This is going to represent high frequency interference, which has short wavelengths. And then we've got white spheres that are somewhere in the middle. So what we're going to do here is dump these in. This is just going to represent interference attacking the system. All right, and just as we expect, you see most of the red ones here, like them being the large spheres. That would signify those long wavelengths, so they're not able to get through these openings. But these short wavelength blue spheres are able to slip right through, get all the way to the bottom here. And actually, do we have one that has slipped through?
I see one came through.
If you can see, there's one that slipped through. We made a couple openings in this bottom, and that is to represent if you have any openings, say your shield doesn't go end to end, or what I see commonly with like a foil shield, if it's in a flexing application and kind of breaks down and makes a crack, now you have an opening and that interference is going to find its way in.
Yeah, it's real good. It really demonstrates how important it is to shield as much of your cable as possible. Make sure it has a complete coverage around the item that you're shielding.
And to choose the right material for what you've got going on. If you have high frequency and throw in some kind of thing with openings, you're not going to see a good effectiveness there.
Right, and you see, all of it's blocked. Some of the blue is blocked even at some of these levels.
Right.
But to get good shielding, you need to block for the frequency you're
exactly.
talking about. And these aren't really, and this is just a demonstration, right? The frequencies aren't the range of these balls, right? They can be really tiny to very large. It's just a good little one. Great, I like that one, Madison. Thank you. Thank you for doing that.
All right. Give Matt a sec to put that down. Sorry about the noise.
This is also, sometimes people talk about it like fish in nets. We had a guy would talk about that, right?
Yep, big nets with big openings is going to catch your big fish, let the little ones through. You need a net with really small little holes if you want to catch a little fish.
The high frequency krill or shrimp at the bottom. You got It's a good analogy.
So however you remember it, those are some good analogies. So that demonstration was actually a great demonstration for shielding effectiveness, which is what we're going to dive into a little bit more now. What you see on the screen here is a shielding effectiveness graph. Sometimes you'll see it abbreviated to SE. And this one, if you see on your y-axis, that left side of the graph, that is going to be the attenuation level. It's measured in decibels or dB. And then on your x-axis, or the bottom of that graph, is going to be your frequency. This one has a range from 100 kilohertz up to 40 gigahertz. A couple things you want to keep in mind when you're looking at graphs like this, say you're looking for a material for your shielding application. You want to find a graph that has a good range of frequencies on the bottom there. Then you know how that shield is performing across a range of frequencies. The other thing you want to look for is multiple data points. You don't want to see a graph with maybe only 2 or 3 data points. It's looking pretty straight. You want to see the performance across a wide range.
So why is it bad to just have a couple data points or straight lines on the graph? Why is it bad?
So if you don't have enough data points, you could be missing a dip, and that would be especially bad if that's the frequency you have. Another thing is either the testing just wasn't very thorough, or perhaps the supplier could be hiding some information from
I
you.
mean, that would be worst case, right? Is they have only a couple points tested and they're hiding a deficiency in
They'll
their shield
pick the
material.
top ones and just make it look really good.
Right. And I mean, that would be very bad. But ideally, you'd see lots of data points tested, and ideally, a couple test points right around the frequency that you're interested in or concerned about, so you know what to expect. To expect 60 dB of attenuation or something right around the frequency you're working on.
Right, and what those decibel levels, what that attenuation level really means is every 3 decibels represents a 50% drop in your interference. So you've got 3 decibels, your interference is cut in half. You go up to 6 decibels, your interference is going to be a quarter because it's now halved again. 9 decibels, you're at an eighth, and so on and so on. So when you're looking at a graph like this one, you're averaging around 60 to 80 decibels, you're left over with really just a fraction of that interference.
Right, and when you look at a graph that shows 60, 80, 100 dB of attenuation, that's not, left over with a 60th or an 80th or a 100th of the power. That's really, because it's a dB scale, it's, a 10,000th or a millionth of the energy that's really left over, right?
Right. All right.
Great, so this is our second demonstration. This is a demo of an actual shield in action.
Yes.
Where we get to see, what it's like to have a signal and then attenuate it with a shield, and what the resulting signals are left over with.
Yes. So I'm going to intro you into kind of the components we got going on here. We have got a signal generator, and then I've got a signal receiver. This is hooked up to the laptop, and I'm going to pull up the screen here in a second, and you'll be able to see a live feed of interference that this receiver is picking up on. We're going to take the generator and dial in at 300 megahertz, but there will be some noise that's also being picked up, but we'll look at that once we get the graph up.
Right, and the 300 megahertz signal is just a generic one that we picked, but it could be, some component in your system is generating noise around there. It's a power switching component or piece of it, or something else that's coming in. You also see that
radio.
Yeah, that megahertz range is also broadcast TV or radio. Also handheld radios generate in that. So it's a common one that we see and run across a bit.
Yep. And then right here, this is our shielding box. You may have heard something called the Faraday cage. This would technically be one. It's a completely shielded enclosure. So like we saw with that other demonstration, how important it is to have a full shield and not have any gaps or that interference will get in. So this is fully bottom, sides, back, and then even along the zipper on the inside, there's an EMI shielded little foam gasket right here to make sure that there's good contact here with the conductive materials, because even the zipper teeth is leaving openings for that interference to get in. So this is giving it just a little something to keep it from getting in. Now I'm going to pull up our live feed. So as you see right here, this is just general what it's picking up in the room. It could be some even Wi-Fi equipment on our production floor. I am going to start the generator, and what you're going to see is a peak right in the middle of this graph.
Yes.
Oop, 1 second. It doesn't look like we are seeing it.
We'll get that graph pulled up. It's kind of neat to see the graph in real time. You
Yeah.
can see some noise generated, then we'll see the signal that we can generate on that receiver.
Okay, are you seeing it now? Perfect. Okay, so this is the noise I was talking about. I'm going to call that the noise floor. Again, just noise it's picking up in the area. And now when I click on our generator and put out that 300 signal, you are going to see a peak. There is that peak right in the middle, and that is at 300 megahertz. So I'm going to stick this into our shielded box, and what you're going to see is that start to go down, and once it's fully zipped, that's going to go all the way down to the noise floor. In goes the generator. As you see, it's already lowering. We are going to get the best shield once it's fully enclosed. And there you go. A full live look at shielding interference.
That was really neat. It was still there a little bit until you kind of...
Until it's fully zipped, right?
all the way over, and then it dropped down. And that peak, I think, was, I don't know, maybe 40, 50 dB
Right.
above where you had the noise floor at. So you
Right.
know, even this simple demonstration shows how a shield can have that much of an effect on a signal. Hopefully, bring it down to
Yeah.
a range where it's not causing problems anymore, right?
Yeah. Yeah. All right.
Great.
And it is really cool to see. I never got to really see anything like that before I worked here.
Yeah, this is great to actually see it in action, to see how the shield is really attenuating
works.
the signal like that. Right. Yeah, that's really great. Thank you for showing us that, Madison.
Yeah.
Great. I think that's the end of what we had prepared as far as content and demonstration, but we did want to leave plenty of time left at the end for questions. You know, if anyone did have questions as we went through, or would like us to go back and talk about any of those items that we discussed. You know, something that we didn't really touch on was grounding.
Right.
You know, that's a question that gets asked a lot, is, you know, grounding on the shields. Madison, you want to tell us a little bit more about, you know, grounding these shields?
Yeah. So I always recommend to ground. It's best practice to ground your shield. You're going to get the best performance once that shield is grounded. But it also works with no ground, as you saw the demonstration we just did. That wasn't grounded, and you still achieve shielding. But good to ground. I do get asked sometimes about grounding on both ends. Is that something that you should do?
Right, yeah. So grounding on both ends is something you can do. We usually just recommend grounding on one of the ends of the shield, because something that you'll hear or we'll tell you is if you ground on both ends, you need to be very careful with how you're laying out your system. You can cause something called a ground loop.
Right.
You know, if the references for the grounds at either end aren't the same, or you have components referencing different grounds, you can cause issues in your system by adding this shield by having two different points. You can have a ground loop and cause other issues by adding this shield. Now you've addressed your interference issue, but now you've introduced new issues.
Exactly.
So you definitely don't want to do that. By grounding at one end, you're still going to get the best shielding performance. It's not going to perform better. Some systems of grounding would require grounding at both ends, but if you're not sure, it's safe to just ground at one end. Leave the other end floating, and you'll get the best performance out of your shield.
Right. Do you want to dig in a little more on those absorptive materials? I like the way that you've described before, calling it kind of a filter, how you can dial in on certain frequencies.
That's right, yeah. So we talked a lot today about reflective materials, the conductive ones, right? Those are the ones that we usually recommend. Yeah, much more common, usually more cost effective and easier to implement, so that's why a lot of people will go to that. But there's also the absorptive materials, right? Those are great in certain situations. And what happens there is those materials, those polymers, those foams that are doped or impregnated with those materials that are going to absorb the energy, they can be kind of tuned like a filter, right? Like an electronic filter, right at a specific frequency. So if you know that you've got a specific frequency that you need to attenuate and need to focus on, you can get a specific absorber for that frequency, which is really nice. Otherwise, you can get more broadband ones, but the issue there is they're not always as effective as a reflective shield. Maybe they'll have 5 or 10 dB of attenuation, whereas you'll get 60 or more with a conductive shield. You can use them in conjunction too. Sometimes you'll see certain areas have an absorber and a conductive shield, just to make sure a specific frequency is handled. And then you have broadband coverage with your conductive shield.
Right.
But it depends on the application. It depends on what your shielding needs or what issues you see or expect to see.
Right. Common with the EMI stuff. It's very dependent on your application, what you choose to shield, what you're dealing with, the results you're going to get.
Absolutely, and that's you had mentioned that before was it's not just dependent on what your frequency is you're going to do. Sometimes it matters what your application is, how you're going to use it, right? If something needs a lot of flexibility or needs weight or needs to be more conductive, you need to weigh all these things when you're deciding on how you're going to shield it and what you're going to use.
Yep, I remember when I first started digging into shielding, and I thought, well, if the foil shield's the best and it's the cheapest, why is that not the go-to? And then you learn flexibility is the biggest thing there. That works if you're going to be stationary, but any flexing, that's going to damage the shield, so you're going to want to go with something else.
Right, and sometimes it's just overkill. You don't
Yep.
need 100 dB of attenuation.
Right.
You know, maybe 20 or 40 dB is all you need, so any shield material will be fine in terms of shielding, and then you would let the application dictate it. Maybe you need
Right.
something that's going to work really well in high temperature, or something that's going to be, you know, used outside, and then then you'll weigh all these things when deciding how to shield or what to do about your shielding.
Right. Any questions coming in the chat?
You know, I don't see any right now, so you know, that's fine. You know, if someone has questions, you know, we'll definitely make ourselves available.
Yeah. You can reach directly out to me and Matt, and we'll
yeah.
be happy to help.
Yeah. So after this, as I mentioned before, you can reach out to us. We'll make a copy of this webinar, a version of this webinar, available for viewing if you did have to step away, or if you'd like to re-watch and see some of those. We'll make the slides available as well, so you can watch those or share it with a colleague that wasn't able to join us live today. Well, on behalf of Madison and myself, I wanted to thank everyone who tuned in today. We appreciate it.